A very good morning to every one of you. My name is Woon Seng. I'm currently leading the Smart Nation Lab at the Nanyang Technological University in Singapore. Today my talk is on the digitization of urban sound in a smart nation. My talk today will cover the following key points: why digitization of urban sound is important, how digital technologies are being used in smart sound sensing, control of noise propagation into residential home, evaluating human sound perception, what are some of the common results, conclusions, and future work. Digitization and digital technologies are now playing a central role in mitigating the negative impact of urban noise environment. Here we take a holistic approach in tackling the three main blocks of sensing, control, and human perceptions that can benefit from the digital technologies to achieve a better urban sound environment. Before we go into the details on digitization of urban noise sources, let me briefly touch on the vision of Smart Nation in Singapore. In Singapore, being a city-state, we call ourselves Smart Nation, and using Smart Nation technology to support better living, stronger communities, and more opportunity for all. However, the main purpose is not a demonstration of high-tech gadgets, but to use technology to solve citizen problems and address existential challenges. Therefore, our Smart Nation vision is to develop and deploy citizen-centric technologies to help our citizens. In order to do this, digitization of urban environment data is key to our understanding our complexity and the demand from our citizens. Today, I'll be describing our projects that evolve around the urban environment sound and the ability to sense, control, and evaluate. I believe everyone is familiar with this type of urban noises. WHO calls it the most underestimated threat for short-term health problems like sleep disturbance and annoyance affecting attention, and long-term health problems like heart disease and hypertension. Next, I will show you some of the examples of how international communities are trying to sense and mitigate noise. For example, there are several noise sensor installations in different parts of the world. These installations in New York City basically uses the acoustic sensors to detect construction noise, siren, rubbish truck, etc. There's another installations in Italy that monitor the highway noise using a sound pressure level meters. Another EU projects basically use sound sensing device to hear the environment and change the traffic lights in ambulance favor. There's yet another project in China where they use acoustic camera to detect car horn in highway and penalize the drivers that creates annoying nuisance. In the special issues on acoustic in smart cities, there are more examples of using digital technology for sensing our urban environment. For example, this group in UK basically use smart apps to assess the urban soundscape. Another research groups in Japan using machine learning based scheme for classification of urban sound. We in Singapore, we have a noisy vehicle surveillance to identify noisy vehicles and those vehicles that illegally modify their exhaust pipes and engines. There's another work in France basically using smartphone for crowdsourcing of noise data and checking the accuracy of the mobile devices. From all these examples, digitization and applying digital technology to urban sound plays an important part to sample and quantify the noise information, record the human preference at a location over a period of time, and building a 24/7 digital ear to hear the environment, just like cameras to see the environment. The information can be used for data analytics to understand the soundscape or environment, or apply digital techniques to contain or mitigate noise. I'm going to outline a series of projects that we are working in Singapore that are related to urban sensing, control, and human perception understanding. These projects are also in partnership with different local government agencies and industry companies. The first project is on the intelligent edge analytics for audio surveillance and noise monitoring. The main research is on the development of an edge device that allow us to deploy 24/7 in residential areas to detect key audio events such as congregation, people shouting, object throwing, etc., and its corresponding directional arrival. In the process, we also can get other types of information like the sound pressure level and other noise level indicators. We deploy in common areas that are attached to poles and structures and send back all this meta information to the crowd. So everything ranging from accessing the metadata, pushing codes, programming, and visualization can all be done remotely. In this slide, we further break down the prompts of smart sensing to three main blocks of microphone sensing array, audio signal processing, and deep learning to derive the sound information directly at the edge device, and only sending critical meta sound information to the crowds for archive, for processing, and alerting different agencies. However, it's challenging using machine for environmental sound event monitoring because unlike speech and music, there's no hierarchical structures or temporal dependence in environmental sound. There's also high similarity, acoustic properties among some sound types. There are multiplicity of sound in the environment, making it difficult task for machine to recognize the individual source types. Furthermore, there's no distinctive difference between foreground and background sound objects. Time taken to detect and classify the source is also crucial for fast response. And also for building AI models, we need a very varied data sets so that we can build a good, reliable deep neural network models. So we human has a very powerful hearing mechanism. When you close your eyes, our brains and ear have this super ability to detect the sound types and pinpoint directional sound sources, and ability to recognize the loudness of the sound. The question is whether we can replace our human ears and brain with a microphone and some AI chips to do the same job 24/7 in remote location. The answer is a growing yes, as we have seen some great progress in machine learning or machine hearing in works in different labs, and I will share a work that is being carried out in my labs to do this task. We put together a smart ear device that can be deployed at the edge 24/7 to perform inference of audio events, directional arrivals, and also other metadata like sound pressure level, duration of sound event, timestamp, location, etc. All these functionalities can be built into this low-cost unit. Since we are inferring at the edge, there will not be a need to push all the raw data to the server for analysis. We've greatly reduced the communication bandwidth and latency in responding to any events on the ground. Furthermore, audio signal is less obtrusive compared to the visual signal. The slide shows our unit being installed in the public places and its hardware specification. This is the outdoor setting with several considerations for protection against the elements and the ease of maintenance. We also have built an indoor sensors that can be powered over the Ethernet and can be easily mounted at the ceiling. This slide shows a typical approach in training inference phase of a deep learning acoustic model to recognize different types of sound events, either a prominent sound occurring at one time frame or multiple sound events occurring simultaneously. The jobs of the deep learning model is to extract key features from the raw data and infer the respective sound events. The typical A deep learning model that commonly used in this job is the convolutional neural network. We have also carried out a recent work on a deep neural network based DOA estimators using the ResNet RNN architectures that will extract sound spectrum temporal features from 4 channels of non-planar or linear array elements. This architecture is further cascaded with 2 parallel branches of fully connected neural network to estimate the active number of active source and also the direction probabilities. This allows us to provide a multi-label output of sound sources and direction. We also take further steps by combining subtasks of sound event detection and also the sound source localization into one joint deep neural network as shown to infer the sound class as well as the direction of sound that is coming from. The detail of the combined jointly trained models of the sound event detection and the direction arrival is shown in this diagram. We first of all extract the features based on the MEL spectrum augmented with the magnitude and phase and pass through a ResNet RNN network before splitting into 2 fully connected neural networks to predict the SED and the DOA. Data augmentation has been carried out by shifting the audio files 4 times to form a larger data size. So this deep neural network architectures consists of 2 stages of ResNet combined with RNN and then 2 fully connected neural network for the respective SED and DOA operation. It is basically a lower complexity compared to the separate models architectures. We also use the same models to participate in last year's detection and classification of acoustic scene and event DCASE task 3 for detecting 11 isolated sound classes which are convolved with the impulse response coming from 5 rooms at 504 locations. So this estimator not only predicts the sound direction, azimuth and elevation, but also the sound label as well as the onset and offset time. We compare our jointly trained model with the baseline network on the validation set based on these 4 performance metrics of error rate, F1 score, DOA errors, and DOA frame recall. And these are the results for the proposed ResNet RNN versus their baseline CRNN performance. And these are for cases where you have single source and overlapping source. In general, our performance of F1 score for the SED is around 0.89 with the error rate of 0.18. The sound source localization error is around 9 degrees with a DOA frame recall of 90%. Next, I would like to show you a video demo on our latest sound event localization and classifier demonstrator. Over here, you see a camera attached to our classifier units and sound coming from these 4 speakers. We have a bird sound coming from the 90-degree speakers. It's being correctly classified as a bird sound 93 degrees. Alarm sound coming from 150-degree speakers is being classified as alarm sound 157 degrees. Next, we have a construction sound coming from 210 speakers. It's being correctly classified and angles of arrival is 217 degrees. We have some object hitting, banging, coming from 270-degree speakers. It's estimated angle 273 degrees. Okay, so you see different types of sound being tested in this demonstrator. So with smart audio sensor, wireless network comes the ability to aggregate meta-source smart data across different sensors. It depends on the need of the application. It can be periodically connected to the cloud and upload recorded information into the cloud database or send alert to operators when needed. This rich information can be consolidated and forms a very powerful database for agency to evaluate different sound analytics indicators visually. So having described the sensing problem, let's move on to another work that we are doing on the digital control of noise that propagates from the external environment into the residential building. Here you see some of the current passive methods that is based on installing noise barrier around the noise source, moving vehicles in the highway. But noise barrier is not a cure-all and only effective for those levels that are within the shadow zone of the noise barrier. Upper floor of the high-rise building are typically not shielded from noise, and noise propagates into the residential building through open window. So the lower right figures you see in here show you the three components of noise at the source, noise path, and at the receiver. There are different approaches to control these three noise components. There are different, and I will talk about how I would attempt to controlling the noise at the receiver, which is the most challenging among the three. The approach that we are using is based on the principle of active noise control. It is a very intuitive approach where we generate another noise to cancel out noise. If our noise source is X, what we basically do is to generate an anti-noise or minus X using a secondary source like a speaker to create a destructive interference. Putting it mathematically is X plus minus X equal to 0. And in physics, you can see that both noise and anti-noise mix in air and cancel out each other perfectly if they mesh in time and space. So ANC has been very popular, successfully applied in noise cancelling headphones as well as reducing road noise in automobile. There are more to the design of ANC. This diagram shows the three main domains in the ANC implementation, starting from the acoustic domain, where the position of the emitter and the internal external error microphone are used to obtain the best noise cancellation. Second, the capture's noise acoustic signal must be turned into digital signal through this analog to digital domain. And third domain, which is the digital domain, is to compute the anti-noise fast enough and send it up to the speakers in time to cancel out the noise. So in order to do an effective job in noise cancellation, the electronic delay must be shorter than the acoustic delay of the external source sound that leak into the ear cup. Any mismatch in time and space will lead to reduction in the noise cancellation. So our project is to scale up the ANC headphones into an ANC for open aperture application. This is a harder problem as we need to take care of a bigger opening of the window compared to the headphones, and this will require multiple secondary sources to provide sufficient anti-noise to cancel out the noise at the opening of window before entering the room. For this reason, the computational complexity of system is much higher and high-end processing capability is needed to sample noise signal at a very high sampling frequency. Since we are dealing with a more varied control environment noise field, we would need to examine the different parameters in determining the most effective way of positioning our secondary source, the physical interspacing between the secondary source, the sensor and the secondary source placement within the windows and under different direction of the primary noise that propagates into the window must be carefully studied through numerical, 2D or 3D simulation. Here you see some of the 2D simulation being shown in this diagram for noise source coming at different angles at different frequency. From the simulation finding, we experiment on the proposed configuration in a real window setting by attaching active acoustic units in the grill. There are two sides to the active acoustic cell unit. The microphone is attached on one side facing the noisy external environment, while the speakers, electrodynamic speakers, which generate anti-noise, is facing inward towards the building. This is the experimentation setup that we have built in our labs to test out the different configurations and algorithms of a multi-channel active noise control system for open windows. So here we have a window opening at one side of the windows, and we put 24 channels of these acoustic cells units, 3 columns and 8 rows, to give us 24 channels of ANC that's running at 16 kHz. We test the interior noise reduction performance of the building under different noise scenario and noise type. Our main target is to achieve a global attenuation without obstructing much of the natural ventilation that comes into the windows. There are more information can be found in these papers. However, there are multiple practical challenges that range from causality issues, where sound waves travel from one end of the unit to another in just 0.35 millisecond for a length of 12 cm. How do we achieve an electronic delay which is less than acoustic delay? How can we adapt to the fast changing noise pattern on the fly? And by using multiple channel active noise control, how do we take care of the high computational loads as well as high sampling frequencies? And also dealing with feedback path from speaker to the microphones, and the amplification of electronic dynamic speakers must not lead to distortion at high amplitude, and the trade-off between using low cost parts and the performance must be considered as well. A conventional real-time active noise control usually employs the adaptive filter x least mean square algorithms to approach the optimum coefficient for the control filter. But this process takes longer time to adapt and is not fast enough to respond to noise changes. Motivated by the practical needs, we propose a selective fixed filter active noise control algorithm. We select a pre-trained control filter to attenuate the detected primary noise rapidly. We first need to pre-train for different bandwidth of broadband noise to build up a library of our control filters. The SFANC algorithm uses a classification scheme that is based on the frequency band match approach to choose the control filters. In this method, the pre-training of the noise to the selected filter has same or almost similar spectrum content to the detected primary noise. For more information can be found on these two papers listed here. Simulation result obtained from the real measurements noise path shows that the SFANC has a fast response time after the initial period of filter selection. In this simulation, we also vary the noise source every 3.5 seconds and noted the faster response compared to the conventional FX-LMS algorithm. In this experiment, we show a series of noise coming from the outside the windows and how much we can reduce the noise after applying the multi-channel ANC. The diagram on the left shows the active noise control off. While we turn on the ANC, you will notice that the majority of the noise field is now at the upper edge of the windows instead at the right and center, and the maximum value of the noise is only around 55 decibel compared to 65 decibel. Therefore, we have a 10 decibel of noise reduction in this experiment. In the final part of my talk, I will briefly outline human perception research and application. So Soundscape started to be a research field in the late 60s and only received significant attention by researchers in the last 20 years in the field of community noise and environmental acoustic. Soundscape is basically defined as the acoustic environment perceived by a person or people in the context of place. Urban sound environment consists of various types of sound that you've seen from the pictures, including not only noise but also human, natural sound and music as well. These sounds have different meanings under different contexts. How do we harness the positive sound and reduce the negative sound is becoming an interesting study. So nowadays there is a paradigm shift from the noise control into a soundscape design. There's an ISO working groups looking into the perceptual assessment of soundscape quality, which I will touch upon later. Conventional noise approach usually tries to reduce the traffic noise by installing noise barriers. Unlike the noise control approach, soundscape designs uses sound as a design element. In particularly, in soundscape design approach, attention maskings by introducing positive sound such as water sound as well as some bird sound is applied to attract the attention of the visitors and decrease the perception of the unwanted sound like truck noise. However, so far there are very few systematic masking research related to practical design. Currently, there are three parts of the Soundscape ISO standard that describe the framework, the data collections, and the analysis of the qualitative and quantitative data. My team has been working on different aspects of the soundscape research, which include the acquisitions of the 3D sound field and on the quality assessment of the acoustic environmental reproduction through virtual and augmented reality headgear. There are several 3D audio techniques that has been applied and conduct psychoacoustic evaluation for masking based on VR and AR tools. Based on the findings of psychoacoustic experiment, we are gathering several design parameters so that we can build a masking system for the urban environment. These are some of the references that you can refer to on our work. A summary of what we have done so far on the soundscape research listed below. We have developed VR AR tools for lab-based tests and in-situ tests in urban environment. We have conducted some psychoacoustic tests that test out the effectiveness of masking traffic noise by natural sound, determinations of appropriate natural sound types and level, validations of 3D audio reproduction for soundscape evaluation, as well as effects of a spatial aspect of masker on maskee. So we are now investigating on different work on validating the masking effects based on in-situ tests, conducting large-scale AR experiment in urban setting, and going to citizen participatory design and public demonstration platform. We are now looking into citizen science, also known as participatory action research, whose outcome provide valuable feedback to our researcher at the same time increase in the public understanding of science. We perform residents' response to the soundscape they are familiar with and seek their opinions on how they feel on the soundscape in their environment through the use of VR or 360 YouTube video with headphones. Through this useful feedback, we can obtain some residential soundscape maps that residents prefer or dislike. There is also another participatory tools for residents to try out different types of soundscape that they prefer and give a rating. Currently, we are working on soundscape apps that enable residents to participate in their daily activities outdoor. To conclude, I have described various projects related to smart sensing, control and perceptual evaluation on our urban sound. They have been carried out in the Smart Nation Lab in close collaboration with local government agencies. The emphasis of this talk is on using different technologies to sense and understand, to control and to evaluate. This digital information is highly important for us to further carry out data analytic research. A key message is that Smart Nation system is not just solely on technology, rather is the individual and society who taps on the technology to make their life more convenient and improve the quality of life. Through citizen science is helping researchers to understand the usefulness of our digital technology. I thank you for your attention.